So if you want to take this from the floor cylinder case, you have to make sure at what temperature you are taking the properties. So in this case, what we have to do is we have to calculate the properties. So TF, let's calculate the TF is 130 plus 30 by 2, that is 160 by 2, which is 80 degrees centigrade. So you have to get the properties at T infinity, and you also have to get the properties at T wall. Also you have to get the properties at T F. Okay. So these are the three cases which you should keep in mind. Okay. So this is at 30 degrees centigrade. This is at 130 degrees centigrade, and this is at 80 degrees centigrade. So for this, what you have to do, you have to go to the data book, go to the page number 42 for air. So it is here. So for each and every case, you have the property values here. You have to substitute them appropriately, right? So let us look at the leave this place aside and move to the calculation of the Reynolds number, Nusselt number, and so on. Now let's look at the formula first and then come to this. See, move to the page number 124. In page number 124, you have this formula. Let me copy down this formula so that I can calculate the H value. The NUD is equal to C into RED power M into Prandtl power 0.333. So this is the correlation here. You got it from page number 124 and it is from 2.1.1. Writing this is good. This reference number, if you write while preparing for exam, it will be easier for you to prepare. Right. So this is the correlation here. You know that in this correlation, you have H and which has to be found out, and the remaining things you have to find out. So he has given a D here. See, this is very important. Previously, in external flow problem itself, we were using HL by K for Nusselt number. Okay, but here he has given Nu with suffix D. What is the meaning of it? You have to use it as HD by K, not HL by K. If you use HL by K, it is not correct. Okay, HD by K is the correct thing. Right. So that is one thing there. And coming to C, what is the C values? The C value will depend on the value of Reynolds number. If the Reynolds number is falling in this range, you will choose this. If this is this one, like that, corresponding C value you will choose based on the Reynolds number. Okay, that is regarding the C. Again, it is bought from the data book, same 2.1.1. And then you have to calculate the Reynolds number. Regularly, you have to calculate the Reynolds number. And here for the Reynolds number, the formula is again, it is VD by nu. Okay, you should not use VL by nu here because VL by nu you will use in case of a flat plate external flow problem. But here it is a cylinder external flow problem, you have to use VD by nu. And the Prandtl number you will get from the data book. So That is the thing here. So in order to proceed with this particular correlation, what you have to do first, you have to find out the Reynolds number value. So how do you go about finding the Reynolds number here? The Reynolds number is equal to Vd by nu, and the velocity is given as 6, and the diameter is given as 0.2. Nu value is unknown to you, and in the data book he has given that these properties are to be evaluated at TF. Properties at TF is given in the data book itself. So properties at TF. So you have to get the properties at TF itself. The TF value is 80 degrees centigrade. For 80 degrees centigrade, what is the value? You refer to the data book and tell me. For 80 degrees, you need the value of nu. It is 21.09 into 10 to the power of minus 6. 21.09 into 10 to the power of minus 6 meter square per second. That is the mu value. Substitute that here, 21.09 into 10 to the power of minus 6. Tell me what is the value of this Reynolds number here. Please calculate and tell me this value of Reynolds number. Yes, the Reynolds number value.
56899.
56899.
0.00427.
0.00427. If this is the Reynolds number value, so you can see the ranges for the Reynolds number here. So here the value is 56,000 change. The Reynolds number value is 56,000 change. So 56,000 change will fall under this category. That is 40,000 to 4 lakh category. So in between 40,000 and 4 lakh, here 56,000 will fall. So the C value should be taken as these two. So from data book, what you get is the C value is equal to 0.0266 and the M value is equal to 0.805. This is the C and EM value. Now that you know it, you know the power and C values. The Reynolds number is also known to you. You have to get the Prandtl number value. So for getting the Prandtl number value, again you refer to your data book at 80 degrees centigrade. 80 degrees centigrade, the Prandtl number value is 0.692. So write that 0.692 here. The Prandtl number value is equal to 0.692. So you're done with your left hand side of the equation. On the right hand side, sorry, right hand side is done. On the left hand side, you need the K value. So K also you get from the data book. So the K value is 0.03047. The K value is 0.03047 watt per meter Kelvin. This is the thermal conductivity value. So now you can calculate the Nusselt number. The Nusselt number is equal to the C into Re power M into the Prandtl power 0.333. So in this, the C value is 0.0266 and the Reynolds number value is 56,899.00427. Power M is 0.805. And the Prandtl value just now you have taken from the data book, it is 0.692. 0.692 to the power of 0.333. So tell me what is this Nusselt number value?
366.49.
366.49 is the Nusselt number value into h d by d. This is the hd by k has to be taken here, and the h value is unknown. The d value is given as 0.2 in the question. Is it right? Yeah, it is 0.2 meter by the k value you have taken from the data book just now. It is 0.03047 is equal to
Sir,
36.
uh, sir, I got Nusselt number as 158, sir. 158.30.
Let me tell
Sir,
me
it's
what
158, sir, Nusselt number.
Nusselt number is 158. Fine. Tell me what is the value of h.
24.
h h
24.11.
h what is the value?
24.11.
24.11 watt per meter square Kelvin. This is the value of h. But this value of h is based on only one correlation, that is that you have taken. Okay, this is generalized equation. If you solve using this equation in the examination, it's fine. But sometimes you may have to use the other correlations also. So I will refer to the other correlations also. See, in this case, property variation is large due to the temperature variation. So if this is explicitly mentioned in the question, then you have to use this one. This correlation you may have to make use of. So the Reynolds number will vary accordingly. So this is bit different because you have to take the properties of gases at Tf, and for liquids it is at T infinity. So it is based on the question you have to go. So if in the given question he is giving water, what you will do? You will take the properties at T infinity. If he is giving the gases, you will take the properties at Tf. Okay. So since we have taken the air problem here in our question, so the thing remains same because in the question he has given air. But if he has given water, the things would have been different. Okay. Keep that in mind. So that is the thing. Even then, if you have to use this particular correlation, how do we solve about it? Let us write here. The Nusselt number is equal to 0.25 into Re power 0.6 and Prandtl power 0.38 Prandtl F by Prandtl W whole to power of 0.25. Okay. So now here you can see something called as PRF and PRW. What is this? PRF means Prandtl number calculated at film temperature. Can you see this? In the data book itself, PRF is given as a film temperature Prandtl number, and PRW is given as wall temperature Prandtl number. So based on the situation, you have to choose. This is one formula. There is another formula here. This formula is here. In this formula, again, you have mu infinity and mu W. Okay, again, mu infinity is dynamic viscosity at free stream temperature, and mu W is dynamic viscosity at wall temperature. So, based on the range of Reynolds number, you have to make use of the formulas here. Okay, here Reynolds number is between 10 cube means 1000 and 2 lakhs. If it is between this, you can use this. This is 10 to 1 lakh, and the Prandtl number value also has to be taken care. So based on that, you will have to actually solve the problem. Okay. So I'm leaving it for you to solve. So choose it accordingly and solve it for yourself. Even in the next generalized case, you have all this stuff. So with that, I complete the cylinder part. Now I would like to move to the sphere part. Okay. So if you have any questions at this level as far as this cylinder is concerned, kindly raise your concerns. Do you have any questions at this level for this one, the cylinder one? Right. Let me move to, even in the cylinder, one more case is there that I must tell you. That is the flow over non-circular sections. This can also be a question. And this is having formula here in 2.1.2. Flow over non-circular shape. Actually, this is the formula you will use. The C1 and the N, the C1 and the N are to be referred from page number 127. That is here, the next page. So C1 and N you will get based on the Reynolds number range. The Reynolds number is falling in this range for this shape. You will choose this one like that. Okay. So the same shape here. The next one also is the same shape, but the Reynolds number range has changed. Based on that, you will choose the C1 and N value. Here, the D value is taken as the this is actually an elliptical kind of a cross section. If you're taking the minor axis as your D, this is your C and N values. If you are taking major axis as your D, these are the C and N values. This is hexagon resting on its base. If that is the case, these are the C and N. And this is a hexagon resting on its corner. This is the thing. This is a hexagon with non-equal sides actually. So if you take diameter this way, this one. Likewise, you can follow the remaining things also. So based on the given case, you will have to actually solve it for yourself. Now let's move to the flow over spheres. Flow over spheres. Let us move to. Let us take up the problem. This one. Solve for yourselves. We'll be going a bit faster from now on because we have to cover the syllabus in less period of time. Kindly understand that. And if you are having any difficulty, kindly let me know immediately. I'll try to slow down and explain it with a slower rate. All right. So now here in this problem, air is taken. So this is an air question. And whether it is an external flow problem, yes, it is external flow problem. It's flow over means an external flow. And external flow over what? External flow over a sphere. External flow over a sphere is the case here. And this is given the T infinity value. The T infinity value is 30 degrees centigrade. And then the diameter is given as 0.1 meters. So the diameter is equal to 0.1 meter. And the velocity is given as 0.8 meters per second. And the solid surface is at 50 degrees centigrade. So T wall is given as 50 degrees centigrade, and he's asking you to calculate the convection coefficient. That is H value, what it is, he is asking. So it's kind of a similar problem that we have solved for, the cylinder. So let's look at the data book for sphere now. So if you come to this here also you have this. The properties are to be taken at here. Okay, the properties are to be taken at here. So it is explicitly mentioned for each case, and it is not common for all cases, and it is not given at the top like in the case of your external flow or flat plate. Okay, it's a sphere case. So from case to case, the temperature at which the properties are to be evaluated will vary. This is the thing you can see, the T infinity thing is given. So um, now here in our case, he has given air. So what you have to do, you can take this one. Okay, for air, the Nu value, the Nu formula is given here as Nu is equal to 430 plus this thing you can use, or even you can use these two also, this one and this one also you can use, because air is also a gas. So using these three, you can find out the H value, and which one is suiting the actual case, that one you can choose. Okay, if you are going for real time, modeling. Okay, but for as an exam is concerned, you can choose any one one among these three, and you can solve it. Right, and make sure that the Reynolds number is falling in its range, and the Prandtl number will be given sometimes.
Excuse me,
Okay,
sir.
yeah, tell me.
In for air condition, they haven't mentioned any explicit condition like it properties as TF, T infinity.
Yeah, TF only. Here it is TF. All the cases are TF only. This whole thing is TF. Like if it is not mentioned, take it as TF. See, in the second case, you can see that is T infinity. Okay. Likewise, you will be choosing. So even though it is not mentioned here, it is TF only. Like because air is again a gas, isn't it? For gas, it is mentioned. It is TF. So air also, it is also a TF only. So it shows it accordingly. So let me calculate the TF value now. 30 plus 50 by 2, that is 40 degrees centigrade, that is TF. So you may have to take the properties at all the things, that is at T infinity you have to take, and you have to take it at properties at T wall. Also, you may have to take it at properties at T here. Okay, so dedicate a space for this at the top right corner. Then let's move to the correlation. Let us take one correlation here, and that correlation let us use here for solving the problem. Okay, so let us take up the first one. The mu is equal to 0.37 into Re power 0.6. So page number 1, what is the page number? 28, 3.1. The Nu is equal to 0.37 into Re power 0.6. This is your Nu expression here. So for this, again, you need the Re value. The Re is equal to which one we will take here, whether you take VL by nu or VD by nu. Again, it is a VD by nu, it is not VL by nu. Even though it is an external flow, it has to be diameter. For that matter, you will not have any L for sphere. For sphere, you will have only diameter. Okay, you will not have any length for sphere. So if it is a case of cylinder, you may confuse between length and diameter. But for sphere, you have only one characteristic dimension, that is your diameter. Okay. So keep that in mind, and you will substitute the values here. The values of velocity is 0.8, and the velocity of value of diameter is 0.1. New value is unknown to you. You have to get it from the data book.
Sir,
So
velocity
move to
actually 8, sir.
what?
Velocity is actually 8 meter per second.
Really? All right, 0.8 here. Yeah, I'm sorry. It is 0.8 meters per second only. Question, it is given as 8 meters per second. I'm sorry, this must be corrected. Thanks for that correction. And here is corrected. Yeah, that's fine. So let's move to the new value, that is the kinematic viscosity value at the 40 degrees centigrade, that is the TF. So this one. 16.96 into 10 to the power of minus 6. 16.96 into 10 to the power of minus 6. That is the Reynolds number value. Tell me what is the Reynolds number value?
47169.811.
47169.811. That is the Reynolds number value. So now let's get the Nusselt number. The nu is equal to 0.37 into 47169.811 power 0.6. So that is Nusselt number value. Tell me what is this Nusselt number value. The Nusselt number formula will again be H D by K. You will not have any L here. So you have to take H D by K. In this, you need what is the value of K for finding the H value. So for this, the K value of 40 degrees centigrade is 0.02756. 0.02756 watt per meter Kelvin, and then this new value also. This is H into D value is 0.1. Yeah, by 0.027. The K value is 0.02756. 56 equal to Nusselt number value. You tell me.
235.72.
235.77.
72.
Double seven.
Okay. H value also tell.
64 point.
64.7.
64.779
964.
watt per meter square Kelvin. That is your H value. So this is using this NU expression, this particular NU expression. Okay, you may use the other NU expression also and solve it. Okay, it's okay. So where is that? So that you can use this NU is equal to 2 plus this expression is there now. This expression also we made use of. Nu is equal to 2 plus 0.25 into RE plus 3 into 10 to the power of minus 4 into RE power on 0.6 or 0.5. This you can do. Also, you can use the other Nusselt number formula. This is equal to 430 plus 5 into 10 to the power of minus 3 into RE plus 0.025 into 10 to the power of minus 9 RE square minus 3.1 into 10 to the power of minus 17. These formulas also you can use. So these two solve for yourself. Okay. So it's again kind of same thing only. You will have Reynolds number on the right hand side. So you have to substitute the Reynolds number into this, and left hand side again the same story. So H value will be unknown.
Nusselt number vary from the above case?
It can vary. It will
Yeah,
vary.
I got 146 point.
You may get. You may get. The Nusselt number will vary. The H value may vary. Okay. So among that, the highest value is generally taken for design calculation. Okay, solve for yourself. Right. So that is the thing. And what else to be said regarding this? Yeah, nothing seriously. So that's all. And coming to this flow across the tube tanks. Okay. Flow across the tube tanks. This is something like this. See, here this is actually the fourth case in the external flow. Till now, what we have seen is we have taken only one tube, and over that the flow is flowing. Okay, in case of flow or cylinder, only one cylinder is taken. Above that, the flow is there. Okay, this we have seen. But there need not be only one tube. There can be so many tubes like this. Okay, they are arranged in certain fashion, like inline fashion they can be arranged, or also in the staggered fashion they can be arranged. For this, how to solve? So if this is given, how to solve? For that, you will make use of the pitch, that is the distance between the tube tanks in the horizontal direction and the vertical direction. The Nu is equal to C into Re power n formula you will use. The C and N values will be taken from the table given here. For inline, you have the values. For staggered, you have the values. So based on this SL and the ST values, you will substitute them accordingly here in the arrangement. So the x-axis value you will find, and the y-axis case you will find, corresponding C and N values you will find, and the C and N values you will take it and put it in this case of Nu is equal to C into Re power N, and then you'll be in position to solve for H value. So it's again the simple thing, the flow across the tube tanks is actually taken like that. So there can be other cases also here, like 10 or more cases there, less than 10 cases there. So all these things you can do it for yourself. I'm not going to solve any problem here based on this particular topic. See, let me tell you why I have covered all this very fastly. Okay, most of the times in the examination, among the cases given here in external flow, you have like four cases. The first one is flat plate, and the second one is the cylinder. And in the cylinder itself, the subcase is tube tank case. Tube bank or tube tank, whatever you call it. And the third one is PF case. So this is the three cases. These are the three cases in case of an external flow. Most of the times what will happen is the question will you will get from external flow for a flat plate. Most of the times the question will be based on a flat plate case. In exam, these are asked. That's why I have solved so many cases based on a flat plate, and I have shown you so many turbulent case, the laminar case, even in laminar, so many cases, constant wall temperature, constant heat flux case I have shown you. Even in the turbulent constant wall temperature, constant heat flux, the liquid metals case, the laminar is considered, laminar is not considered, fully turbulent. So many cases I told you as far as flat plate is concerned, because all those cases are generally asked in the examination most of the times. Okay, but whereas this cylinder and the tube tank and the sphere is concerned, okay, less in exams. Okay, so that's why I have covered them very fastly. Okay, even I have covered them very fastly. If you know how to use your data book for the flat plate case properly, you can use for this one also. Okay, refer to the notes that I have told you so far in this one. So only thing regarding this cylinder and sphere is the difference is here you may not be taking a TF alone. Okay, the case is different here. It can be for T infinity, it can be for T wall also. The properties will take it. So this is the only difference. Otherwise, the whole thing remains the same. Here you have to take the D value instead of HL by K. You have to take HD by K. In place of Reynolds number, also you will have to use the D as a characteristic dimension. So these are the two major differences. The TF and the D story. So otherwise, it is more similar to your flat plate case. So that's all from the external flow problem. And regarding this external flow problem, someone among you has asked me a question regarding the average value. What is the meaning of the average H, and what is the meaning of the local H? That is actually a very good question. So that will help us understand the concept of boundary layer, which I will be dealing in the next class. But anyways, here you have something called as average Nusselt number, and you have a local Nusselt number. Okay, what is an average H and what is a local H? That is the question basically. See, what is a H value? We have to understand first. Okay, for that, let me take a flat plate case itself. This is a flat plate. On a flat plate, air is flowing over in this direction. Okay. Air is flowing in this direction. So if the air flows, there will be something called as a boundary layer formation. So this is a boundary layer formation. So what's happening because of the boundary layer formation? The velocity of the air is not going to be constant throughout the flow. So if you take this wall here, this flat plate here, the velocity profile will be something like this. This is the velocity profile. So even though you are taking the average velocity and doing the calculation, but in reality, whatever the velocity that is there, it is not going to be the same velocity throughout as far as this boundary layer is concerned. That's why what happens is the velocity is varying. Velocity is varying with length. Since the velocity is varying with the length, what will happen to the H value? See, all the formulas, the NU are related with some Reynolds number. That is, NU is what? It is nothing but your non-dimensional H value. Reynolds number means what? It is non-dimensional velocity value. So H and velocity are directly related here. Higher the velocity, higher the H value will be. So the velocity will seriously influence the H value. So since the velocity is varying here for a given velocity, that is, let us say some sort of velocity Vx here, for this particular velocity, you will having the particular H value here. And that particular H value is called as local heat transfer coefficient. Okay, but you have something called as a velocity which is common throughout. That is the free stream velocity. We call it as free stream velocity. and this free stream velocity is same throughout. So this will represent the average condition of the flow there. So if you are referring to that particular H, that will be H average, or it is shown with H bar also. It is average heat transfer coefficient. So that's how the average heat transfer coefficient and the local heat transfer coefficient differs. The local heat transfer coefficient is referring to a particular location, the properties, especially the velocity. Okay, the velocity is different here. That's why the H value will be different. But average is representing the overall overall mean properties. Okay, so based on the overall mean properties, if you take, it is the average heat transfer coefficient for particular location. If you calculate, it is the local heat transfer coefficient, and the other one is average heat transfer coefficient. I hope the explanation is clear. Somebody asked me this question in the last class or last to last class, whatever it may be. So, you have any questions in this explanation? Is that clear? Who asked this? Rahul has asked this.
Yes, sir. Sir, in a particular location, we have multiple velocities at different layers, sir.
Yes.
Then how would be single H local value?
So that's the point. See, here, even if you take the average value, this average value also is based on all these things. This, so many velocities will be there here. Okay, so many velocities less than this pre-stream velocity are existing in this boundary layer. Okay, here one velocity, here one, here one. Like that, so many velocities are existing. All those velocities are taken as an average here. Okay, see, when I say velocity here, it is need not be a velocity alone. Okay, based on velocity, your temperature will change. Based on temperature, your property values will change for all the things. So what you are dealing with here is very complex phenomenon basically. So your Cp value of air will change, the the fluid's Cp value, the fluid's alpha value, fluid's K value, fluid's nu value. So all these values will change. So there are so many things that are changing here which are not in your control. All these things will influence. So I said the effect of this with a example here, that is a velocity. Okay. So it need not be velocity alone, the property that is changing. There are so many other properties that are changing because of the velocity variation or the temperature variation. Okay. Its effect is not simple thing to correlate here. Okay, it's actually complex to actually find a reasonable solution and an easy solution. This non-dimensional concept has been brought in, and this non-dimensional concept has addressed this issue partially, and it has not addressed this completely. So, and these correlations are helping you find out the H value, which is an approximate value, which is not an exact value. Okay, nobody knows the exact value of H because H value is depending on so many parameters. So finding the H value is always a complex thing. Is it clear?
Yes, sir.
Yeah. So that's the thing regarding this. So I told you that there are three topics in convection. That is internal flow and the external flow and the natural convection thing. So we have completed the first two today. In the next class, I'll be starting the natural convection. Tomorrow morning class, I'm going to start this natural convection. Okay, probably it may take 2 or 3 classes. With that, we'll close the third unit and then we will move to the fourth unit quickly. Fine.